All right, welcome to this explainer. Look, if you're a software engineer gearing up for a system design interview, cramming for a database exam, or honestly, if you just want to finally get a firm grip on how databases keep our data so perfectly safe, you are in the exact right spot. Today, we're going to take database transactions and make them simple, memorable, and totally stress-free.
So let's kick things off with a classic nightmare scenario. Picture this, you're transferring $200 to a friend. The database deducts the $200 from your account, but right at that exact millisecond, bam, the power goes out, the server crashes. When it finally reboots, your money is just gone. But your friend, they never actually got it. This is the absolute catastrophic reality of a partial update, and avoiding this exact disaster is the entire reason we have the concepts we're diving into today.
Here's our game plan for today. First, the distributed nightmare. Then, atomicity, all or nothing. Third, consistency and isolation. Fourth, durability, surviving crashes. Number 5, we'll take a look under the hood at write-ahead logging. And finally, number 6, we'll wrap up with acid versus base trade-offs.
All right, part 1, the distributed nightmare. Now, before we look at how to actually protect our data, we really need to nail down what a transaction even is. Because it's not just a single command. In database land, a transaction is a sequence of operations, reading, writing, updating, deleting, that are all bundled together and treated as one single indivisible logical unit of work. For us as software engineers, the main goal here is maintaining data consistency and reliability, even when our environments get, incredibly complex.
And to guarantee a transaction doesn't just corrupt your data when things crash, database management systems stick to 4 core properties: atomicity, consistency, isolation, and durability. You probably know them as ACID. Let's break these down one by one.
Moving on to part 2, atomicity, all or nothing.
Let's see how our very first letter, A for atomicity, completely solves our little bank crash nightmare. The absolute most crucial point here, and this is an exam key phrase you'll definitely want to remember, is all or nothing. Atomicity essentially means a transaction is indivisible. Either every single operation inside that transaction succeeds completely, or absolutely none of them do. There is no halfway.
Just contrast that disaster of missing funds with the safety net of a full rollback. Think about it. If we deduct that $200 from account A, but the credit to account B fails because of some random network glitch, atomicity kicks in. The entire transaction rolls back. It undoes the debit and restores account A to its original balance. It's an absolute guarantee that we never suffer from data-corrupting partial updates.
Okay, part 3, consistency and isolation. What's really fascinating about this next pair is how they enforce the rules when multiple users are hammering the database all at the exact same time. Let's talk consistency. This ensures that a transaction only ever transitions the database from one valid state to another. It strictly enforces all your defined rules. Things like foreign key constraints, data type validations, all your business logic. So for example, if a rule states account balances can never go negative and a transaction tries to overdraw an account, consistency steps in, forces an abort, and reverts everything right back to the previous valid state. Then we have isolation, because in the real world, hundreds, maybe thousands of transactions are happening concurrently, right? Isolation makes all these concurrent transactions appear as if they are executing sequentially, just one right after the other. It acts kind of like a brick wall, making sure transactions do not interfere with each other. It uses mechanisms like locking, ensuring that users never get a sneak peek at each other's half-finished work. Now listen up, because if you've got a system design interview coming up, you absolutely need to memorize this trade-off. You've got the 4 standard isolation levels and the specific read phenomena that they prevent. At one end, we've got read uncommitted, which gives you maximum concurrency but leaves you wide open to issues like dirty reads, meaning you might read uncommitted data. But as you tighten things up toward serializable, you get complete strict isolation that blocks all those phenomena, including phantom reads. The catch? The big trade-off is performance. Strict isolation locks up resources, which drastically reduces your overall system concurrency.
Next up, part 4, durability, surviving crashes.
This is the final letter of ACID, and it kicks in the exact moment after you hit the save button. Durability means exactly what it sounds like. Once a transaction is successfully committed, its changes are permanently saved. They're never lost. I mean, even if someone literally pulls the power plug on the server right then and there, or the system suffers a catastrophic crash, your data is totally safe and sound. And that is vital, because memory is highly volatile. A system failure can be triggered by a random processor bug or just a simple power outage that instantly wipes everything in RAM, which, let's be real, usually results in you getting paged at 3 a.m. Because of this reality, the database requires robust extra measures to make sure it can actually recover to a consistent state after the hardware completely fails. Think about the exact millisecond a system crashes. The transactions that were fully committed before that moment, say transactions 1, 2, and 3, those are durable. They absolutely must survive. But the transactions that were still mid-flight, those have to be safely aborted, and their partial effects completely erased, so they don't corrupt anything when the system eventually restarts.
All right, part 5, under the hood, write-ahead logging. So how exactly does a database pull off all this durability in Atomicity magic when the actual hardware is so incredibly unreliable? Well, first, we have to understand the strict lifecycle states of a transaction. It always starts out in the active state, just doing its normal reads and writes. Once those operations finish, it moves to partially committed. But watch out, changes are still only in memory at this point. The truly critical jump is over to the committed state, which is where changes actually get written to permanent storage. If an error or a crash happens anywhere before that, the transaction goes to failed and then it's aborted, rolling back completely.
The real engine that drives this whole life cycle is write-ahead logging, or WAL for short. Before the database makes any real changes to the primary data files, it writes a sequential record of the changes to a separate log file first. And it crucially records both undo and redo information. That way, if a crash happens, the database just reads this log upon restart. It uses the undo info to roll back any of those incomplete active transactions and uses the redo info to reapply the successful ones that maybe didn't quite make it to the main disk yet. But what if your data lives on 3 totally different servers? Well, this is where the two-phase commit protocol, or 2PC, comes into play. A coordinator node asks all the participant databases to prepare, and they all vote either yes or no. In phase 2, if even a single node votes no, maybe because of a lock or a constraint, the coordinator sends out a global rollback. It requires unanimous yes votes across the board to send a global commit. And that is exactly how we ensure atomicity across entirely separate distributed databases. Which brings us to part 6, acid versus base trade-offs. And this perfectly sets up a classic system design interview question. When do we actually choose not to use acid? Well, per the CAP theorem, systems have to trade off between consistency and availability during network partitions. ACID strongly favors strict consistency, which makes it the undisputed gold standard for relational SQL databases running heavy-duty financial or banking software. But BASE, which stands for Basically Available, Soft State, Eventual Consistency, that model highly favors availability. You'll see this used in NoSQL databases like DynamoDB or Cassandra. The base model willingly sacrifices immediate consistency so that things like global social media feeds or massive e-commerce sites just never go offline, even under truly massive load. Which leads me to this final thought. As a software engineer designing the next massive application, you really have to ask yourself, is the strict locking and overhead of ACID a genuinely necessary gold standard for your specific data, or is it just a bottleneck that's going to completely crush your system's availability? Understanding exactly when to rely on ACID and when you should embrace the eventual consistency of base is pretty much the hallmark of a great system architect. Thank you so much for joining me on this explainer, and hey, good luck designing your next architecture.